invitation. It's a real pleasure to be here. What I want to talk about today is Legendrian knot theory. It's sitting inside of the standard contact structure on R3. So this is really sort of the ground level of Legendrian knot theory. So we're just thinking about R3 with a contact structure given by the kernel of this quad form, dz minus y dx. Let me say that I'm going to use the projector to project some pictures that are best shown rather than hand-drawn during a talk, but there won't be a lot of words on here. And so if you want, because some of these notes that you might take won't make sense without the pictures, I can give you those digitally after the talk. So if you're interested in the pictures. And I should say that all this is joint with Dan Rutherford, who I see is just right. And so he's at Arkansas, and we've been doing this for the last year or so. And the paper is also on the archive of the same name. Okay, so we're thinking about Legendrian knots. So that's a knot in R3. This is not Legendrian. Its tangent space sits inside this contact structure. All right. So this gives us sort of a geometric criterion for our knots. No longer are smooth knots sufficient. We now need that their tangent spaces sit within this contact structure. And so to show you what the contact structure looks like, well, if we think about this room as the board is the xz plane and y is going into the board, then right in the board, they're all nice and flat. They're parallel to the floor. And as I move away from the board, sort of out in this direction, they turn clockwise. And as I move into the board, they turn counterclockwise. This is all invariant to the z direction. So if you want to fill this out with all the planes, you just sort of move these up and down, and that gives you all the planes. And so we need that our knot at every point, its tangent direction at that point is sitting inside this two-plane field. All right, so the useful projection for us is called the front projection. Although there are two useful projections, we'll stick with the front projection today. And that's literally just projecting onto the board, projecting onto the xz plane. So the front projection of L projects onto the xz plane. And so instead of having nice smooth curves in the plane, we end up seeing these cusps because, of course, if we're going to be tangent to this two-plane field, we can't ever point exactly in the z direction, because that's not an option in our two-plane field. And just given the direction these planes turn, we know that if we have a negatively sloped part of the curve, that always appears in front of the board, and a positively sloped part of the knot is on the back side of the board. So we work with these projections, and we have a nice Rademacher theorem that allows us to say, well, if you're worried about Legendrian knots up to isotopy, Legendrian isotopy, well, you can look at these front projections and get between them with some Rademacher moves. So in a lot of ways, this added structure refines smooth knot theory, so it's no longer sufficient to say, well, this is a triple, this is an unknot, they're different. Now, within any one of those classes, you have infinitely many different Legendrian knot types. So we can have lots and lots of different unknots. And so the game becomes, how do I distinguish these? How do I distinguish two Legendrian knots that are smoothly isotopic, so they're both trefoils, figure eights, whatever. So that's really the game, and so there's a few approaches. This is sort of considerably younger than smooth knot theory, and so there aren't nearly as many approaches to how you find these invariants. There are what are called the classical invariants. Rotation number and thirst Dominican, which are just numerical invariants, which are very useful distinguishing lots and lots of, well, that's how you can see right away that there are infinitely many different unknots, Legendrian unknots. There's this theory that centers around generating families, although that's also called generating functions. So I'll use the term generating families. I don't see a lot of Russians, so I don't think I'll upset many people, but you more often see it as generating functions in that language. Symplectic field theory really kicked off, what I would put in quotes, the modern age of Legendrian knot theory by giving us our first differential graded algebra that allowed us to derive a lot of nice computable invariants. And then in recent work, there's been progress made using Heegart floor theory. So there's not a lot of techniques to tackle these questions of how you distinguish isotopic, well, the sign of two Legendrian knots of Legendrian isotopic, but there are a number of techniques. So we're going to center our attention around these two. This was the geometric motivation behind symplectic field theory was really a floor-theoretic geometric motivation, which led to an algebra, a differential graded algebra, from which we derive all these invariants. So this has been a very robust area of work. And on the other hand, generating families, where this is floor-theoretic, this has been largely studied using classical Morse theory. So the invariants we derive here have also been useful, and sort of what's been happening is finding connections between these two. It turns out that many of the things you find over here are connected to things over here, and we're going to continue that line of work today. So what we're going to do is derive a differential graded algebra that's motivated by what's going on with the Morse theory in a generating family, and then we're going to show that this is connected to what's going on with the DGA on this side. So that is the game. So what's a generating family? Well, this is a generating family, and it's easier to sort of visualize it first and then write down a definition. So I have some front projection. This is an unknot. You can see that you could easily untwist this if this were a smooth knot. And what we have here is a sequence of functions. And the functions start to the left of the knot projection, and to the left of that they're nice and linear. There's nothing going on here. This is just a function from R to R. But what we see here is that as I pass through this cusp, the birth of two critical points occurs. Okay, and those two critical points correspond to these 2 points right here. And so as I move from left to right, what I'm seeing is the evolution of a one-parameter family of functions, where when two canceling critical points are born, I see a cusp. And when they move further apart, we'll see I'm actually graphing here the critical values. So as the critical values get further apart, the actual strands get further apart. Then I introduce two more canceling critical points that correspond to this cusp right here. And you can see the order. This is the top guy. This is that guy there and here, and then down the bottom right there. And then when I have a crossing, what's happening is that two critical values are changing place. So the top guy and the third guy are just changing place, and that's how I end up over here. And so this evolution continues with the death of two critical points and then the death of two more critical points. And so this is a generating family. It's a one-parameter family of smooth functions that as it evolves, it gives you the front projection. Okay, so let's write down sort of a more formal definition here. So what this essentially does is it completely encodes the front projection, and it actually encodes the entire knot. And so if you want to study Legendrian invariants, you can sort of study these functions and try to derive algebraic invariants using Morse theory. So it's a function f. This first r component that we think of as just the x-axis. And then I have some fiber component, which I'll just call it e, to r. Okay. And I'll leave a space here for some words I'm going to add. Is a generating family for a knot L. And I'm going to be a bit sloppy here. I'm going to let L denote both the knot sitting in 3 space and its front projection. Here I'm actually talking about the knot sitting in 3 space. Okay, so the generating family for L, if, so I have 3 criteria here. So this is the fiber critical set, which I define to be, it's the ordered pairs x, e, such that the partial in the e direction, well, there's actually n partials there, they're all 0. Okay, so if you fix a single x, let's say I fix this one right here, then I'm looking at these 4 points right here. Okay, there's where my partials are all 0 in the fiber. Okay. This must be a one-dimensional submanifold. Of the domain. That's to ensure that our next criteria actually gives us the knot. This says that L is exactly the set of points x, the partial in the x direction of f at some pair xe, and f at xe, that's a triple, sitting in R3, such that xe is in as this critical fiber critical set. So if you ignore for a second that we've projected away the y component, this just says it's all, the front projection is just pairs x and then the critical value of f of x comma e. Okay, and so that's why I'm saying this is really the graph of the critical values. For each of these points, both these points sit in the fiber critical set, and they correspond when I graph them to their critical values. Okay, and then finally, just to maintain. That's okay, actually. I can see it from there. That's good. To keep things nice, I want that this is linear outside of a compact set. So this function is just a linear function. Outside some compact set of domain. And that's what you see right here. As soon as we get past the cusps, I just want this to be sort of a front projection that's contained between two vertical lines. Now, if you want to work over S1 or something like that, then you have to change that. But so this is a generating family. And the whole goal for today is to derive algebraic invariants from this. Derive sort of algebraic objects that we hope that will be invariants. And so what we do is we look at this and we say, well, for each one of these slices, I can get a chain complex because each one of these is just a Morse function. And as long as I have some nice generic metric, then for most of these, except for that sort of critical points where things are born or die, I can get a nice Morse function. And I can get a chain complex. So this is Voronekov's notation for the chain complex that corresponds to this guy right here. And let me walk through what this notation is doing. So the chain complex is generated by two critical points. There's one right here and one right here. And I have one flow line going between them. Well, what this notation does is, for each of these vertical lines that you see, this indicates a grading. Okay, so this is the grading 1 vertical line. This is the grading 0 vertical line. I have one grading 1 critical point, index 1. I have one index 0. And this line between them says that the differential applied to this generator is just that guy right there. Okay, so this is a shorthand. So if I let, that's a poor choice. Let's go A1, A2. If these are my two generators, then the boundary of A1 is equal to A2. And for us today, we're working mod 2, so we only care about these things. If we were working over Z or something else, we'd have to assign numbers here to indicate how many flow lines there are moving between these two critical points. But for us, it's just Z2. And so that gives us a chain complex.
And the grading is always the Morse index?
In this case, it is, yeah. When we actually do invariance, we'll have to shift to a grading shift to take into account that if you sort of isotope this and you continue the generating family, the indices might change. But for us, yeah, let's just think of it as the Morse index. This gives us a sequence of generating chain complexes.
Are you also keeping track of the the order of the generators?
Yes.
That's also important.
Voronekov's notation also keeps track of the height, the order of the generators. Yeah, so it's always sort of moving down and to the right.
So the height of the critical point is according to their critical value?
Yes, exactly. The height of the critical point is according to the critical value. Okay, so then if we move over one, then our topmost critical point is right here. The next one is here. These are both Morse index 1, so they appear right here. I have one flow line from the top to this third guy, and I have two flow lines coming out of this guy, one to the third guy and one to the fourth guy. Okay. Now this can sometimes happen. So when you're when you're creating two new canceling critical points, you have two cases. Basically, they appear far away from everything else, and then you just see a single gradient flow line between them. That's sort of what happens here. Is they're just born, no one's around, so they have no interactions with the other critical points. Or what's happening here is that these were born into the mix, sort of already into the flow line that was going from here to here, and so it's very easy to algebraically write down what's going on there. There's essentially some instantaneous handle-slide moves happening right at that cusp. Okay, so we have here sort of a way of deriving a sequence, a finite sequence of Morse complexes. And that's actually, this idea is due to Peter Pushkar, who thought that this would lead to some nice invariants, and it has led to some interesting things. So it turns out that you don't even need all of this to keep track of what's going on here. So it's sufficient to introduce these little marks. These little marks indicate that as I move past this cusp, essentially what it's saying is these guys weren't born in isolation. They were born, but at the instant they were born, there were these handle slides that happened. And so essentially we would see, sort of in the instant of birth, a gradient flow line from this critical point to this critical point. They're the same index, right? So this is essentially a handle slide.
Sort of a feature of being very low dimensional in this
Yeah.
example, right?
Yeah.
Like low index.
Yeah, we can sort of move these things away, and that's what we'll do in a minute. So by introducing these three marks, I'm essentially encoding all of this data. Because I know that if I don't see any marks, then my bursts are really just simple. They just, two new critical points are introduced. There's one gradient flow line between them. And then as I move past these guys, I know what the handle slides are. I'm encoding the handle slide data. And so I don't need any of this. And so essentially this is encoding a generating family. At least if you're given a generating family with a sufficiently nice metric, you can write down this thing. Okay. Now, this gives us a set of algebraic criteria to use to build these, even though we don't necessarily have generating families. And then the question is, when I build these algebraically, am I building something that has a geometric analog? So that's always sort of the key question that's sitting here. So let me write down something to slow myself down. So this is called a Morse complex sequence. And I'll abbreviate this MCS from now on, just because it's a mouthful. So I'm going to use the notation script C. I'm going to leave it blank here because I'll tell you in a second what this actually is. Well, one, it has three sort of properties. It includes a set of handle slides. And I guess I really should tell you what this is. So this is a triple. Of a collection of chain complexes, a set of x values, and then a collection of handle slide marks. So you need these x values to sort of divide up the x-axis into places where you see chain complexes. You need the handle slides to tell you, when are these, during this evolution of the generating family, at what point do I see a flow line between two critical points of the same index? We know that that is, generically that would happen in a one parameter family, so we have to keep track of those. And then these are just a collection of chain complexes, so that these guys down here. So I call these handle slide marks, and they'll appear either as dotted lines. Dotted lines are the instantaneous ones that happen at critical points or at cusps, but we'll also see that you can see them away from cusps as well. So x1 through xm divides L into elementary pieces. Well, what I mean is that between any two of these vertical lines, I see a single cusp, a single crossing, or a single handle slide. Okay. And then 3, we have a sequence of chain complexes. There's 1 attached to each of these x values. And then, like I said, in a generic one-parameter family of functions, you would see certain algebraic behavior in the chain complexes. And all we're doing is saying, well, it has to obey the algebraic behavior that we would see in such a generating family. So we're not saying that every one of these corresponds to a generating family, but we are saying that what this is encoding is the behavior that you would see in a generating family. Okay, a sequence of chain complexes with consecutive complexes related by chain maps determined by the knot, the front projection, and the handle slides.
Did you say that it's possible that you could come up with one of these MCSs which is not
We don't know.
realizable?
We're not sure. I'm not sure. There are some special forms that we can put these guys in. We can move these handle slide marks around and put them in a position where we know we can produce a generating family. There's an equivalence relation that I haven't said yet, which allows you to move these marks around. But we're not yet sure that if you just gave me one of these MCSs, I could produce a generating family. Or we don't even have examples where we know we can't produce a generating family.
Can't you recover where the H's are from the sequence of chain? Like, you can see 2 next to each other, don't you know there must have been an H?
Yes, but you don't know. In fact, you don't always, because there are certain situations where a handle slide doesn't change the chain complexes. That's the annoyance.
Yeah.
Otherwise, we would rather, yeah. So you don't always, you can't sense the handle slides just from the chain complexes. Okay.
I think there's something. What are the handles that you were citing?
So I'm not showing them, but and let me show the next example that it better indicates what's happening here. Here's a trefoil. Again, here's an MCS. So I see a division of the x-axis as a front into elementary pieces. Now right here, between these two right here, okay, what I have here is that this is indexed 2, 1, 1, 0. And I have an instant during this generating family, which I'm thinking about exists, but it may not, where I have a flow line between that guy and that guy. Okay. Now, generically, if you just take a Morse function, that won't happen. But if you sort of take a one-parameter family, you could run into that sort of behavior. And so this isn't, what would happen is that you would have a flow line right from here to here, and now this guy would then be able to flow down to that one, produce this gradient flow line. So that's the behavior that we're abstracting. Okay, so this actually has no implicit, that's what we use the word, handle slides happening at the cusp. So if you look at it, whenever 2 are born, they're born sort of in isolation from everything else. These 2 guys are born in isolation from these 2. And then I just sort of have some swapping here because of the crossing. I have some more swapping there because of the crossing. Then I finally see something interesting, a handle slide. And then I swap, but then this handle slide sort of undoes what that one had done. And so when I go in to die, they die sort of alone, well, in pairs. It's a very sad. Okay. So this is a nice form. We call this an SR form because it relates to switches and returns that you would see in normal rulings. So if you know what that means, essentially I'm saying there's a switch right here because this guy is sort of cordoned off by these 2 handle slides, and that there are no switches here or here.
Can I ask a specific question? Why do I call it a handle slide? I lost it.
So this goes back to the Kirby calculus, right? The way you slide a handle over another handle would
I don't
create
see
this.
it.
Why am I using this term?
Yeah.
Think about it as like a, this is a Morse function on R3 now, right? Right. And so it's got, at first it's just got index 0 and 1 critical point, and then you got 0 and 1 and 1 and 2. Or I guess it could be on R2, right?
Right.
And then you've got somewhere in the middle there, you've got a one. Those 2 horizontal things are one handles, and there's a slide of a one handle over another one handle.
it's for the critical points that you're sliding.
Yeah.
Okay, critical point, you're trying to find critical points.
Well, flow line
It's the same
from.
thing.
Sorry.
Okay. All right. Let's see what All right. Well, I said that there was a choice made when you write this down. So if you have a generating family, you have to choose a nice metric that allows you to write down this MCS to get these chain complexes. And so there was a choice made when we wrote down what exactly this Morse complex sequence would look like. And so to take into account the fact that you can change the metric, we have an equivalence relation. And so the equivalence relation, essentially, you can write it down as a sort of combinatorial thing working with the handle slide marks. Okay, so if you change your metric, you may see a change in the Morse complex sequence that looks like one of these. Okay. There's a few interesting ones. Let's see. This one's somewhat interesting. We slide these two. You introduce another. We also allow ourselves to take an explicit handle slide that's happening sort of away from a cusp and sort of ram it into the cusp and make it implicit. So we make it so that what was maybe before sort of a nice birth that happened far away from everything else, we can sort of make it ugly by sort of pushing these handle slides into the cusp.
You mentioned you're only changing the metric in these equivalences, but if you wanted an invariant, you'd want to change the front, and
Right.
then you have like dovetails and so
Right.
on.
Yeah, yeah, and you can control, if you sort of move all the handle slides out of the way and do your dovetail, you can say what's going to happen in the algebraic features. Writing down the propagation of MCSs through a front change is sort of long and tedious. It's not been done.
So you need to do it to show it's invariant. Oh, you.
I'll show something else as an invariant. We actually end up showing something as an invariant by passing back to the symplectic side. The DG, the Chekanov-Eliashberg DGA.
What's the difference between the and the
So the dashed arc, essentially, what's happening is that the dashed arcs are sort of handle slides that happen right at the instant of death. Okay, this guy has the freedom to sort of move away. This guy is sort of stuck at the cusp. Practically, in terms of what's happening with the algebra, nothing is changing. Okay, but this is sort of the more geometric behavior that you would see if you were sort of, there's a way to untwine a birth and to make it sort of disjoint from everything else that's going on, and you can reverse that process. So if you want to, you can take a birth or a death and sort of separate it from everything else, or you can sort of incorporate it into what else is going on. So that's what's happening with the dotted versus the solid. Okay. Any other questions? 3 questions. All right. So the point of this whole program is to start with the generating family, pull out useful algebraic data, and then produce some Legendrian not invariants. And so one not invariant that has already existed and been used successfully is called the generating family homology. And so let me just say what that is, and we can actually start working with, we can translate it over into the Morse complex sequence realm and actually lift it up to a full DGA rather than just a homology theory. So what we have here we have what we call the difference function. So we still are thinking about having a fixed generating family. So I have some fixed generating family big F, and I take this difference function. This is X, this is E1, this is E2. We think of these together as the fiber over X. And we just take the difference of our generating family at these 2 points. XE1 and XE2. And so the homology of this, well, a certain type of homology, the generating family homology of this generating family is this gradient shifted homology relative Z2 homology. And let me write it and then I'll say what this is. we're essentially looking at the inverse image of everything greater than some fixed delta relative to W equal delta. And delta is chosen, it's positive, and it's chosen so that between 0 and delta, there's always critical points at 0 with critical value 0, because you can just pick, say, one of these critical points right here. Let's say this is xe1. I can put xe1, xe1. Okay, so that's going to be critical value 0 if I put the same point into both, and it's going to be a critical point. So, so we choose delta just sort of close to 0 so that this contains no critical values. And so the set of all these things over all possible generating families that you might have for Legendrian knot is an invariant. So as you sort of isotope the knot, you can continue these generating family homology groups through the isotopy. Okay? And there's a grade shift that's required because as you do that isotopy, you might have to change the fiber, you might have to add dimension to the fiber to get the generating families to continue. Okay, but you can see this. So here's some generating family homology. We can see this with a certain chain complex. And the point is that we can see the chain complex on this Morse complex sequence. So the chain complex I'll write with this notation. It's generated by, well, the critical points of this difference function whose critical values are all larger than delta. Okay? Okay. The question is, can we see these critical points in our front projection, and can we see the flow lines that allow us to compute the homology in our front projection? So that's sort of the question. Can we see this on the front projection? And the point is, if we change the front projection using Lenny-Ying's resolution procedure, we can see it. Okay, so Lenny-Ying's procedure says, well, I've got 3 rows here. So the top row is sort of just the front projection. The bottom row is the Lagrangian projection, which I'm not talking about today, so you can sort of safely ignore this. And then the middle row is what the procedure does. And the procedure changes the slopes of these strands. So it starts to the far left of the front projection. It starts stretching these things out. And the point is that it stretches them so that the slopes decrease as you go from top to bottom. And then what's happening here is that right before you get to a crossing, since these slopes are decreasing, these two guys have to change slopes. And when they do, you get this point right here, well, 2 points. We have an instant where we see the same slope at these 2 points. And the same slope indicates that they have the same y coordinate when you pull them back into 3 space. And so that's why in Lagrangian projection, which goes to the floor, you actually see the crossing here and not here. The point is, if we do this for the entire knot, it becomes possible to see the generators of this generating family homology. So I'm stretching this knot, and now my generators, well, they're points, they're pairs of points, xe1 and xe2. These themselves, because this is going to be a critical point, this has to be a critical point of big F. Okay, well that means that it has to be one of my points on these strands. Okay, so xe1 has to correspond to a point on a strand, xe2 has to correspond to a point on a strand. And the fact that it's a critical value of W means that they also have to have the same slope. Okay, and the only places where I see that are these two together will give me a generator. These two together will give me a generator, and those two together will give me a generator. Okay. So it does correspond to the right cusps. You see that for this right cusp, I end up with this generator. For that right cusp, I end up with this generator. And for the crossing, I end up with this generator. So it does correspond to the right cusps and crossings. And if you've worked with the Chekanov-Eliashberg DGA, that's a good thing because that's what they use too. If you look at the reformulation of the Chekanov-Eliashberg DGA on the front, that's exactly the generated set.
Is it sort of like you perturb F,
Yeah, you will
so
also
that
have to
W is a Morse function and has isolated critical points, is that, or so that it's just easier to see the
So they're easier to see is
I see.
what I'm doing, yeah. I'm gonna pass back to this.
Oh, I see. There
picture.
may be lots of places in that top picture with the same slope, but
Yeah,
they're not
yeah.
horizontal slopes. You
Right.
want a horizontal, yeah, I see.
Right, yeah, the point is to sort of, I want that away from these positions, all the slopes are different, so I can't possibly have a critical point. I can't possibly have a generator. So this description allows me to see the generators, and the question is, can I see the flow lines? Because I can see the generators now, and they correspond to right cusps and crossings. Can I see the flow lines? And so let's see if we can do that. All right. The goal here is that once we see the flow lines, we'd like to pass the flow trees and actually create a differential gradient algebra rather than just a chain complex. And so the goal is really, can we see the flow lines with the hopes of seeing flow trees? All right. So the motivating question for the next 10 minutes is, can we see the flow lines on M? Okay. Well, we can. We think we can. There's a reason why the title includes the word combinatorial, because a lot of the geometry behind this, we're using the geometry sort of as a metaphor or inspiration, intuition, but we haven't firmed up a lot of the analysis behind this. So what I'm showing you is the intuition that we use to formulate a completely combinatorial DGA. So we're going to stretch the metric. So what do I mean here? Well, we have some metric on our domain, R cross Rn cross Rn. And I'm going to break it into these two pieces, one that's a metric on the fiber and one that's a metric on X, on the R piece. So given this, and some S between 0 and 1, we let G sub S be the metric G sub R plus S G sub the fiber. Okay, so what are we doing here? Well, if we look at the gradient, let's say we look at the gradient at time 1. Well, this is just G sub R plus G sub F. This is the gradient we're trying to understand. If we look at that at some point, and let's say it has the form alpha beta, where this is sitting inside the tangent space at X of R crossed with the tangent space at E1, E2, at Rn cross Rn. Sorry about that. Well, then if this is the vector, the gradient vector at this point, with the metric where S is fixed as 1, then when I slide 1 to just be some S between 0 and 1, I stretch the metric in the fiber direction. So what I'm doing is I'm taking and stretching the gradient in the fiber direction. So for each of these fixed x's, I'm going to stretch it in that direction. Okay, the point is, let's see if we can see this. The point is, if I want to understand how to get from here to here, well, this is G1. And this is going to end up being something close to G0. What I want to do is stay on the front projection. Well, the front projection is the graph of things that don't ever point down. So it's really this stuff up here. And so as soon as I come off of these two horizontal lines, I can't see what's going on in the front projection. The point is to stretch the metric so that I'm almost always staying up here, and at certain instances I jump down, and I continue along the front projection. Okay, the point is to sort of isolate what's happening with these gradient flow lines into just a sequence of jumps. And so when we go to the limit, we can write down what this should look like combinatorially. We know what the behavior should be. The question is, can we find S that's sufficiently close to 0 where what we think it should be is what it is? Are we geometrically getting the right gradient flow lines when we do this? So that's really sort of one of the big analytic questions still remaining is, are we counting the right things when we pass to our combinatorial description? Okay, well let me show you what this looks like on the front. As I said, you can actually see this. All right, so this is three cases. Here's a crossing, and it's in formation, so it's been stretched and the slopes have been changed. And so I know I have a generator right here. Okay, so this is a generator.
Not a hand slot.
What's that? Not a handle slot. That's what these little knobs mean now. So if you see these knobs are generators. Now if this generator, let's see. I need to write down one more thing before I start talking. S of W is going to be tripled. X E1, E2, where X E1, X E2 is in the fiber critical set. Okay, so what is this? This basically says that if you pick some X coordinate, and you have these two fiber coordinates, then they should correspond to 2 points, 1 point on one strand, 1 point on another. Okay? This is the set of points in our domain that we can actually see on the front projection. We can see them. They're just, for any 2 points you see, like this point and this point, are connected by a strand, that corresponds to something in this set. And what I'd like to do is keep my gradient flow lines in this set as much as possible, and to limit their jumping to happening at very specific times. Okay? So if I want to stay on this set, what that means is that when I move, I have to sort of visualize this critical point, which is itself an element of this set, sort of moving and staying on these strands. Now if it moves to the right, nothing interesting happens because it quickly gets below delta. Remember that we fixed delta to be above 0, so if I move to the right, nothing interesting happens. So I don't move to the right. There's no gradient flow line there that's worth looking at. Again here, I don't want to move to the right. So all this is going to be happening from right to left. And I should say that, to be technically correct, we're assuming that our front's in flat position, just so I don't have to worry about moving any of these by right cusps. You know what that means? Just take it. Now, the problem is, when I jump along, when I do one of these instant jumps, I might change my index of the critical point. So the index is really just the difference of the Morse indices of these two strands. That's just what it is. It's just a difference. And so when I jump, I have to be careful that I don't reduce my grading, my index, too much. Okay, I really only want to reduce it once, right? I'm trying to go from a critical point of, let's say, index 3 to something of index 2. Okay, well, the only time that that can happen, the only time that you can jump down and get to another critical point is if when you jump, you land exactly on a critical point. Okay, and so as you pass through, the only time that can happen is as you get past a crossing, right at this instant where there is another critical point, if I see a fiber-wise gradient flow line, I jump along it and I stop. Okay? So that's what's happening there. I start with one of my generators, and I start moving it to the left, and then to end at some other critical point, there has to be this moment where I instantaneously jump along a fiber-wise gradient flow line that reduces my index by 1 and lands me exactly on another generator. And so we don't work with these projections, these stretch projections very often, so this is what it looks like if you just translate it combinatorially to what's going on sort of normal front projection. So I start with my generators just next to the crossings and cusps, and if I want to end, remember there's a critical point right here, if I want to end there, I have to see this fiber-wise gradient flow line. Okay, so now I should say one more thing, and that is, you can have an instantaneous jump that doesn't change your index. And that will happen if you see one of these handle slide marks. Okay, the handle slide mark allows us the opportunity to jump without reducing our index. And so, what does that look like? Well, most of these are uninteresting. If I'm sort of moving along, I can sort of continue without doing anything. But what's interesting here is with these marks, which indicate flow lines that don't change index, I can jump along them. Okay. And so if you want to count the actual generating family flow lines, you need to count them allowing for these jumps.
So this picture doesn't have any critical points of W, right? Just pieces of flow line.
Yeah. This is just happening away from the critical points of W. So these are the rules. Like I said, this is all just sort of an abstraction and a combinatorial description of what we think is happening in the generating family homology. The point is that now that we can sort of see what's going on with these rules, can we do this for a metric tree? Here's a full path, actually, if you want to see it. So I started at a critical point, I sort of increase, I increase again, nothing interesting is happening, then I jump, and then I die. So I go into a critical point.
Sorry, this is a flow line from one critical point, which is
Yeah,
the
the
right.
critical
Where's the
point
other
that-
critical point?
Right here.
Ah,
Yeah. You would, so it would look like, this is the last bit of it.
oh, because the critical point's past the.
It just passed it, yeah. Yeah, it's on the left, yeah. Okay,
Can you go back just a bit?
yes, sorry,
5 more seconds.
sure.
Okay.
Okay. All right, so successful work has been had using flow trees in Morse functions to add algebraic structures like cut products and things like this. So that's what we wanted to do, and this idea was sort of given to us by, yeah.
And in the picture where you're at like G.001, if you're really, it's almost
Yeah, it's almost
basically-
there.
So how many times are you going in the phi direction in that example? Just once? Or are you basically just going along the front direction and then at the handle side
Yeah,
you go
You dive
the
down.
fiber?
yeah.
At the handle slide and at the last group.
And at the last critical point, yeah. So the jumping down happens either at a handle slide, a fiberwise handle slide, but it always has to happen at the critical point you're going into.
Why couldn't it just happen somewhere else?
Because the only way, the arrangement of, oh, good question. So there's no way to sort of land on one of these because it's right next to a crossing. There's no way to land on one of these without jumping along a gradient flow line right at that instant. And that will necessarily decrease your index. So you only get to do that once. Now, when we start looking at, so we have to prove some things at some point, right? So when we're proving that d squared is 0, you do allow these exceptional jumps along gradient flow lines in the fiber away from these crossings. And sort of that's the one-dimensional moduli space that sits between two broken flow lines. You allow that exceptional step. But when we're just writing down the zero-dimensional moduli space, you only have this at these crossings. Okay. So the game here now is then to try to form a full differential graded algebra on the tensor product of all these critical, right constituent crossings by looking at metric flow trees. So what's happening here is that you have lots of Morse functions. For us, we have lots of generating families, but it'll turn out these are all essentially the same generating family, just shifted something. And you flow sort of in the gradient of one, and then you sort of branch off and flow in the gradients of the others, and this has to sort of happen continuously. So let me just write down, say something about what these W's are. So I'm going to do an easier tree. So we're going from one critical point, let's say A, and it splits and ends up at 2. And I end up with these three different gradients, W13, W12, W23. And so what are these functions? Well, they're just essentially the same generating family as before. The difference of it, this is X, this is E1, E2, E3. W13 is X, E1, E2, E3. It's just the difference of X, E1 minus X, E3, and plus some non-degenerate quadratic involving whatever extra variables we have. This gives us a way of assigning, so essentially the same but also a functionally different generating family to each of these edges. Okay. And by using the same stretched metric, we can actually see what this would look like in the front projection with the MCS data. So let me say what that's going to look like. So there's a split at some point, right? So at some point you're sort of working along nicely. We're thinking about this stretched metric so we can actually see what's going on. We have these chords that are moving from right to left. And then I get to this point here and I have to branch. Well, what this should look like is that this chord, this long chord, just breaks into two short chords. Okay? And then they continue on. The problem with this is that these both have to end somewhere. And when they do, they're going to have to do so by jumping along a fiber gradient, a gradient flow line in the fiber, which is going to reduce their index. So their index will be reduced by 2, which we can't have happen because we're trying to look at sort of, we need the index of B1 times B2 to be 1 less than A. So I can't let these both jump along some gradient flow line in the fiber. Which means that when I actually split this up, one of them has to die immediately. It has to go right into a critical point. And what that means is that what looks like a long sort of flow line would just be a constant point. So when you split, one of them has to immediately go into a critical point. And so what that looks like is that the split has to happen right as you pass a crossing. And one has to stay there and the other keeps going. And that's an index argument, essentially, as to why that has to happen. So using this, we can actually give a description of a differential gradient algebra. We can prove that that b squared is 0, using essentially combinatorial analogues of what would be moduli space arguments. So let me state the theorems because we're basically out of time. And then if you want to ask a lot more about this, you can see either Dan or I, or both. So this is joint with Dan. So for each MCS, there's some algebra which is generated by the left cusps and crossings, right cusps and crossing. There's some differential which counts these flow trees given combinatorial rules that we get like this, and this is a DGA. Okay. In a minute, I'll tell you how this connects with the Chekanov DGA, because it does. Okay. So the other, the second theorem is if I have two MCSs, if they're equivalent, well, I'd like to say something about the full DGA. I'd like to say that the full DGA is sort of chain isomorphic in some way, but we can't do that yet. We don't. That's actually an open question for us. I can say that that their linear terms are chain isomorphic. So if I look at D1 in each of these, They're chain isomorphic. And sort of the last result, which I'll just say because I'm basically out of time,
Okay, what does equivalent mean?
up to those combinatorial moves that I showed earlier. These guys. So basically, we just think of these as changing the metric. There's a special form. There's two sort of useful special forms for these MCSs where you move the handle slides around and put them in a form that allows you to say something about connections with the Chekanov DGA. And so there's something called the A form, which you can think of as sort of just taking all your handle slides and trying to ram them all to the rights. And when you do that, it's easy to show that if you put something in one of these nice forms, there's a bijection between these nice forms and augmentations of the Chekanov-Eliashberg DGA. And once you have that bijection, it's easy to show that when you take the Chekanov DGA, Chekanov-Eliashberg DGA, and you do a change of basis using the augmentation, you get exactly this MCS DGA. They're equal. Okay, so the MCS DGA for an A form is equal to the change of basis you'd use with the augmentation to get a DGA with the Chekanov. And so let me just say what the open questions are for us. One is how much of this is geometrically faithful, and you can see I had a lot more to say. You can ask me about that if you want. Does every MCS come from a generating family? And is our combinatorial procedure geometrically sort of accurate? And then what happens in terms of the equivalence on MCSs with the full DGA? And I'll stop there.
So I missed what you said at the very end. Did you say that you get when the calculation works with Chekanov equal?
Yeah. You take the Chekanov-Eliashberg DGA and you do the change of basis with the augmentation. And it's equal to that in the DGA with this bijection between A forms and augmentations. Yeah.
So these the diagrams lines, they don't tell you the dimension of your generating family, right? So
No.
There's the equivalence moves that they have that also so if they do some equivalence dimensions, the move can still.
Yeah. So there's there is an equivalence here where you could sort of add a non-degenerate quadratic to both generating families to make the dimensions line up, and then you can work from there.
Okay, and then that doesn't change.
No, it doesn't change the marks. I did leave off a move that's sort of complicated and interesting called the explosion move. That's Pushkar's notation. And so I did cover up a lot, but there's that there too that I'm not saying anything about. Yeah.
So, you demanded that your generating families are linear at infinity. I mean, is that the series restriction? Can you do anything saying it's quadratic or cubic at infinity? And I assume those are more general families, right? I assume you get anything that's linear, you could probably get with the quadratic, right? But you could probably get more, or is that not? No.
No, it's they're just if you want me to.
Please.
Okay. So if you want to generate compact Legendrian, you better have linear at infinity. If you have quadratic at infinity, then your Legendre is going to be non-compact. It'll be like a long Legendrian.
Critical points outside.
Because you'll always have critical points. Yeah, as David pointed out, you'll always have critical points for any x in your base manifold. And you also don't want to go and you don't want to go higher than quadratic. The second you go higher than quadratic, you suddenly can't really do the Morse theory anymore. You don't have a globally defined Morse flow. So you only want to be quadratic or below, and linear quadratic generating families give you completely sort of different families of Legendrians.
So maybe I'm misremembering something, but I remember at some point maybe Giroux saying something that if you don't demand the fixing things at infinity, you could kind of realize almost any Legendrian, with generating families.
Oh, but that's sort of allowing degenerate at infinity as well, not just.
Oh, I see.
These are all sort of non-zero linear, and I think if you allow zero linear, then you can probably do. I'm not sure, but
it's not unreasonable that you can do anything. Okay. Okay.
Any other question? Thank the speaker.
And I think how you can